Hello, and welcome to 5G Enabling Technologies, MIMO, Multi-User MIMO, and massive-MIMO with Professor Abbas Omar. I'm Mike Hamilton, your host for this IEEE Microwave Theory and Technique Society webcast, which is sponsored by National Instruments. Before we start, I'll mention a few housekeeping items. First, this presentation will be archived. A recording should be posted approximately 24 hours after we finish the presentation. We'll send all registrants an email when the archived webinar goes up, so you can revisit it or share it with your colleagues. Second, we encourage questions. We'll answer them after the talk, but you can submit them at any time during the discussion. Enter your question in the Q&A box in the webcast window, and don't forget to click Submit. Third, some words about the interface. You can enlarge slides by clicking on the rectangle at the top right of the slide area. You can also go into full screen mode if you desire. Refresh or reload the current page if you encounter any problems. With regards to audio, if you're listening over your computer speakers, you can adjust the media player volume. You may also need to adjust your system's master volume. The icons at the bottom of the webinar window include a resource list. Clicking that link will start the process to download copies of the slides to be presented today. Now let's introduce our speaker. Professor Omar received the Bachelor of Science, Master of Science, and Doctor of Engineering degrees in Electrical Engineering in 1978, 1982, and 1986, respectively. He has been Professor of Electrical Engineering since 1990 and Director of the Chair of Microwave and Communication Engineering at the University of Magdeburg, Germany, since 1998. He joined the Petroleum Institute in Abu Dhabi as a distinguished professor in 2012 and 2013, as an organizer of the research activities for the oil and gas industry in this area. In 2014 and 2015, he chaired the Electrical and Computer Engineering Department at the University of Akron in Ohio, USA. Dr. Omar has authored and co-authored more than 450 technical papers extending over a wide spectrum of research areas. His current research fields cover the areas of microwave, magnetic resonance and acoustic imaging, microwave and millimeter wave material characterization, phased arrays and beamforming, massive MIMO, indoor positioning, subsurface tomography, and ground-penetrating radar, as well as field theoretical modeling of microwave systems and components. He is also an IEEE Fellow. So now it's my pleasure to turn the virtual podium over to Professor Abbas Omar for 5G Enabling Technologies, MIMO, Multi-User MIMO, and Massive MIMO. Abbas?
Yes. Good morning, everyone. This is Abbas Omar. My talk today is a general overview on MIMO, multi-user MIMO, and massive MIMO. This is the outline of my talk for today. After a short introduction, I will talk about the wireless channels as linear time varying systems. I will move to the concept of conventional MIMO, multi-user MIMO, and massive MIMO. And then I will give some words about the 5G standards and specifications, emphasize the massive MIMO for 5G, and I will move to phased array and beamforming and multiple signal transmission. But at the end of my talk, I will have a short comparison between all digital beamforming and phased subarray before I conclude my talk. So let us first go to the definition of single input, single output, single input, multiple output, single input, multiple input, single output, and multiple input, multiple output. This is actually related to the channel. So if we say single input, single output, it is single transmitter and single receiver, and so on. Why do we use such configuration? This is actually for creating multiple channel transmission, so that we can have more than one physical channel between the transmitter and the receiver. And this will help us in either in spatial multiplexing in order to raise the data rate, or if the bit error rate of the transmission is not good enough, we can make use of such resources as a source of diversity. So in these aspects, we should compare between, or we should include in our discussion, the attributes data rate, bit error rate, and channel coding. In order to be specific, let me first consider the single user. So actually, we have the whole resources for a single user. If we have a high signal-to-noise ratio, this means we have a low bit error rate, and we may put these resources, I mean multiple channels, for increasing the data rate through multiplexing. So we can subdivide the entire data rate into sub-data rates and send or transmit each sub-data rate through a channel. If the bit error rate or the bit error rate is high, so we may make use of these resources for spatial diversity, which means we send the same data multiple times and add the received signal together in order to increase the signal-to-noise ratio and to decrease the bit error rate. There is another aspect which should be included here, which is the channel coding, because if we include channel coding, we actually inflate our data, so by adding some control or parity bits, and this will result in decreasing the data bit error rate. So actually, on the one side, we inflate the data, but on the other hand, we may use of these resources coming from the multiple channel transmission in order to accommodate such a higher data rate with the final effect of decreasing the bit error rate, the data bit error rate. Different scenarios will end up in different results. No one can say, okay, what's better to make the multiple channel resources for diversity or for together with the channel coding for increasing the throughput. So actually, each situation is particular in itself. For multi-user usage, so we may make use of the multiple data transmission for serving more than one user. Let me move now to the model of wireless channel. A wireless channel is actually, or the best model for wireless channel is linear time varying system. In order to just saying some words about this model, imagine that you excite a system this which is shown to you here as impulse response h of t and t dash. So you excite with the input signal x of t and you have the output signal y of t. In general, if you don't have the linear time invariant system, so the each time you excite the system at say t1 dash, you get a different response. This is the general case. And if you would like to see the output signal, so it is just a convolution between x of t dash and h of t and t dash. For the special case of linear time invariant, the h of t and t dash is just a function of the difference between t and t dash, which is also called delay. So the importance of such a model is shown in this view graph, in this slide here. Because if you perform a double Fourier transform, because now you have two time variables. One is a real time measured at the receiver, and the other one is the delay tau, which is simply the difference between t and t dash. Now, with these two time variables, you may have a double Fourier transform giving rise to two frequencies. One is the classical frequency, which I call f, and the other one describes actually the time variation of the channel, which is denoted here by nu. And if you look to the double Fourier transform, which is shown to you here on the left-hand side, the linear time invariant case corresponds to infinitely high mountain, which is infinitely thin. Can you imagine this mountain here is infinitely high and infinitely thin. And if you increase the time variation of the channel, the mountain itself becomes lower and becomes thicker. So it is actually the thickness of this spectrum in the two-dimensional case is a measure of the time variation of the channel. Just to give you an example of that, imagine, just consider the Doppler effect. If you have moving transmitter and stationary receiver, or moving receiver and stationary transmitter, you may easily show that the double Fourier transform H of mu and F is given by the forms you see here. And if you look to the F mu plane, the Doppler effect is just to have this infinitely high mountain, so just rotated by an angle which is proportional to the speed between the transmitter and the receiver. And if you have multiple motion, so imagine that you have multiple reflection, and these multiple reflection are with moving targets with different velocities. So in this case, you will cover the space shown here in the figure on the left-hand side. So now let us come to the general model of linear time varying system. The general model for a wireless channel. A wireless channel is, as I told you before, linear time varying system. If you make a snapshot of h of t and t dash, which I showed you before, so you will have a fixed h of tau. And now with the multiple snapshots, you can imagine that you have a dancing h of tau. So the time itself is your variable, and you have a dancing h of tau. For the most simple wireless channel model is just to assume that you have multiple reflections, one coming to the receiver after time tau1, the other one after time tau2, and so on. And the strength of these multiple reflections are different. And this is actually if you have deterministic case. But because you don't know where is your reflectors, and where are, if you are in indoor situation, where are the moving people in your vicinity, and so on. So you can imagine that these Dirac deltas here are dancing in both directions, in the tau direction and in the vertical direction E1. Just you can, this is actually a stochastic model for the channel. And of course, if you have infinite bandwidth, you will have a series of Dirac deltas. For finite bandwidth, these Dirac deltas will be widened as shown here in the left. So this is the very, very simple model for wireless channel. Because we don't have a deterministic phenomena, we are dealing now with a stochastic phenomena, we should actually describe everything as a random variable or as a stochastic process. Just to refresh your information about stochastic process, the stochastic process is shown here in the curve on the left-hand side. You will have a bunch of functions, x of t, denoted here by x1, x2, and so on. If you stay at a certain time instant t naught, you will have a random variable with a certain probability distribution. If you just catch one of these functions, or one of these sample functions, so you will have a time function. So as you see, you have actually two dimensions here. One dimension is a time dimension, in which you just consider one implementation of the phenomena, x1, x2, or xn. The second dimension is to stay at a certain time and to say, okay, I have now a random variable. Therefore, you have two types of averages. You have the statistical average, which is shown in the first line. This needs the probability distribution. The second one is a time average. And in order to make our life simple, one assumes that the phenomena, in this case, the communication phenomena, is ergodic. Ergodic means that whether you make your average on the statistical basis, as shown in the first equation, or on the time basis, as shown in the second equation, you will have the same result. Of course, there is no proof that wireless channels are ergodic. the whole thing is a little bit different because you assume that it is ergodic and you try to find out results. If these results are coincident with the observations or experimental measurements, it's okay. If not, you return back to your model and try to fine-tune it by, say, relaxing this ergodicity. Okay, I come now to the concept of MIMO. Imagine now that at the transmitter side, you have an antenna array, which is shown here as transmitting array, and at the receiver side, you have another array. If you actually have just one path between the transmitter and the receiver, the array will not help you at all because the transmitted signal is a linear combination of the different inputs to the elements of the transmitting array. Just a linear combination. And this linear combination will come to the receiving array. The different antennas in the receiving array will receive this linear combination just once. The difference between one receiving antenna and the other is just a multiplication factor. Therefore, if you just have line of sight communication, the concept of MIMO doesn't work at all. But now imagine that you have just one reflection in addition to the line of sight. The line of sight itself will transfer a certain linear combination between the antennas of the transmitting side. The other path will give rise to another linear combination. And now every individual receiving antenna will multiply the first path by a constant, which is different from the constant by which the second path is multiplied. So in other words, the antennas at the receiving side will have two different linear combinations, which means they can now resolve two signals at the transmitting side. Now you can generalize this concept by increasing the number of multiple reflections. So in this case, you may have at the receiving side multiple linear combinations of the signal sent by the transmitting side, and this is actually the core idea of MIMO. Let me try to. This is just a very simple equation. Pk in your in the first line here. This is path number k. As you see, it is just linear combination of the sent signal xm, and what each individual antenna yn receives is another linear combination of the different paths. If you put these two equations in each other, you will have some sort of channel matrix which relates the received signals n to the transmitted signal m. In the general case, or in the ultimate case, that you have multiple reflections from all directions, all space directions, you just replace the summation by integration, and what is called channel matrix, which is I indicated here by H and M, is now an integration. I will not go deep into the derivation of these equations. You can have it quietly at home. I will just concentrate on the final result. But I tried here to make the derivation as clear as possible for those of you who are willing to follow this. I will move now to the conditions put on the distance between the different antennas in the transmitting or in the receiving array, because this will show us afterwards why should we go with the frequency higher for mobile communication. In this simple case, I assume multiple reflections from all directions in space, which I characterize by xi. So in this case, you have multiple reflections from each angle xi, and the let me go to the expression itself. No, I'm sorry. I'll go back. Here you have the you define two angles. One is the transmitting angle theta. It is given by the equation in the lower left side, and the receiving angle phi. If we so again, I will not go into the details of this analysis. What is important for me is, let me skip this, and is the expression of the channel matrix. If you look here, you have the received signal from Y1 to Yn, the transmitted signal from X1 to Xm, and this expression H11 and so on, these are the elements of the channel matrix. And these elements, in order to see whether the matrix itself can be inverted, because an important condition for having multiple beam transmission is the invertibility of the channel matrix. Based on this simple analysis which I'm showing to you here, I try to look to the condition of linear dependency or linear independency between the different rows of such a matrix and the different columns. So if you consider the two spaces, one is the row space and one is a column space, you may define an n-dimensional angle between the different vectors. So each column is a vector in n-dimensional space, each row is a vector in n-dimensional space, and you may now discuss or investigate the linear dependency between the rows or in the or the columns by just considering the n-dimensional angle between these. And if this angle is far away from zero, the rows or the columns are linearly independent. If these angles are very, very near to zero, the corresponding rows or angles are rough or nearly linearly dependent. Of course, in order to have the full strength of a MIMO, we should have the channel matrix connecting the transmitting antenna to the receiving antenna invertible, which means all rows are linearly independent, all columns are linearly independent. So based on this simple analysis here, you can follow it. It is actually not difficult to follow it. Let me come to the expression here for the angle, the n-dimensional angle between two rows NL. So it is the Bessel function of the argument, the difference between the nth row and the lth row, times twice pi the distance between the receiving antennas and the receiving, or between the antennas and the receiving array. The same applies to the different columns. It's again the Bessel function of the argument itself, the difference between the columns, nth column and k column, times twice pi dt over lambda. Just to show you what does this mean, if you look to the expression or the graph of Bessel function, and you say, okay, I would like to have, say, J0 equals 0.5. Why 0.5? Because 0.5 is actually cosine of 60 degrees, and the 60 degree linear, I think that the two vectors with 60 degrees between both these are enough linearly independent. If you now transfer this very, very simple equation into how much should be the spacing between the receiving elements or the transmitting elements, it's something like lambda by 4. So if you work within this limit, so actually you may have, if you have enough multiple reflection, you may have linearly independent rows or linearly independent columns of the channel matrix. Let us see now what does this mean now for a mobile unit. Nowadays, if you look to LTE or 4G, so we work around 2.5 gigahertz. So the corresponding quarter of lambda is 3 centimeters. And within a mobile unit, which is shown to you here on the left-hand side, you may accommodate something like 2 antennas. I don't think that you can accommodate more than that. If you now raise the frequency to, say, 5 gigahertz, I just used here nice numbers. It is not necessarily what is going to be the case with 5G. It's just nice numbers with nice values for lambda. If you now go to 5 gigahertz, the corresponding lambda by 4 is 15, and you may have up to 4 elements within the mobile unit. If you go to 30 gigahertz, and this is actually the new radio in 5G, you will have lambda by 4 is 2.5 millimeter, and in this case, you may have up to 24. And this shows to you one of the advantages of raising the frequency. So, of course, besides other advantages, but one of the advantages is here is to accommodate as much antennas as possible within the mobile unit. So, as a general rule, this is the expression for any element of the channel matrix. Again, we need to have invertible, so no zero determinant, invertible channel matrix. These are the elements of the channel matrix. The K parameter here is the number of independent multiple reflections. The rank of the matrix is a minimum between the number K of the multiple reflections, the number of rows, and the number of columns. If you have 4x4 MIMO, but you have only 2 independent multiple reflections, the rank is 2. If you have 100 multiple reflections, but M is 3 and N is 5, the rank is 3. So the rank is the least number, and the rank is at the same time the number of independent channels which you can have between the transmitter and the receiver. Okay, let me move now to the multi-user MIMO. So the base station in this case uses antenna array in order to serve multiple users. The whole idea is much more matured in the area of Wi-Fi. In Wi-Fi, we have nowadays for maybe less than $100, you may have an access point working with N and AC and working also with MIMO. For 802.11n, you have maximum of 2x2 or 4x2, which means the base station has up to 4 antennas and can serve users with up to two antennas. For the AC, we have up to 8 antennas at the base station. Okay, let us move now to the mobile. This is still, I'm sorry for that, just for Wi-Fi again. For Wi-Fi, you see here in the picture in the bottom, a base station with 4 antennas, and it is assumed that the channel matrix is invertible, so that you can also generate from these 4 antennas 4 data streams. And now the first data stream serves iPad or tablet, and the second one is a smartphone, and the third and the number 3 and number 4 both are serving a laptop. So this is one of the scenarios which are actually currently applicable. Let us go now to the mobile communication. It's a little bit different. In 4G, which is known also as LTE or LTE Advanced, one distinguishes between the open loop, in which the channel state information are used as the user unit or only, or the closed loop, in which the channel state information are known as both at the mobile unit and the base station. We have different standards for LTE and LTE. They are described by Release 8 and Release 10. All of these are details which we don't need within the context of this webinar. Important is to know that Release 8 for LTE allows for up to 2x2 for download only, which means the base station can generate 2 independent data streams serving 2 different users. LTE Advanced allows for 8x8, also only for downstream. Let us move now to the concept of massive MIMO, which is intended for 5G. Massive MIMO means now the base station is going to use up to 1,000 elements. So 256 element array or 1024 element array. So just an inflation or just having a large scale of the small scale used in multi-user MIMO. These are two figures here showing you the difference between the current 4G, in which the base station is capable of producing a maximum of, say, 2 independent data streams serving just 1 unit, and the future 5G, in which the base station is capable of simultaneously producing multiple beams. These beams are serving multiple users. The user can be served by just one beam if its need of data is moderate. It can also be served by multiple beams. So the resources at the base station can be distributed between the users depending on their needs. This is actually what is intended for with massive MIMO for 5G. This is here the cellular topology. I don't think that it is important here. This is a possible scenario for the size of antenna arrays. So we may have at the base station up to 256 element arrays, and in the mobile unit something like 16 antenna arrays. But as I showed you before, this necessitates that we should go with the frequency high. Let me give you a very, very quick idea about the target specifications of 5G. It is intended to have a cell capacity of something like 20 gigabit per second for download and 10 gigabit per second for upload. The density, which means how many devices can be served by a single base station, it is called here IoT devices because it is not necessarily your smartphone. It could be sensors, it could be something else. So the general term here is IoT devices. The density, the targeted density, is something like 1 million per square kilometer. We also target very, very high mobility for high-speed trains up to 500 kilometers in an hour, high-speed vehicular access. Latency is also very, very important and very, very critical attribute for many applications. The targeted latency is less than 1 millisecond. The spectral efficiency, and you can achieve this spectral efficiency only by using MIMO. For the download, we need something like 30 bit per second per hertz. This number is actually how many bits can you assign one symbol. And for the download, the target is 30. For the upload, is the target is 15. And it is intended to achieve such spectral efficiency by using something like 8x8 MIMO for download and 4x4 MIMO for upload. This is just to show you how arrays look like. I borrowed these pictures for some universities and some colleagues. The first one on the top is linear antenna array, in which the elements are rectangular patches. The second one is two-dimensional antenna array, planar. The same applies to array C. Array D is a cylindrical array, which is more suitable, say, for masts for base stations. So this is the future of mounting the arrays. So this is just fantasy now. You making use of big buildings in order to mount these big antenna arrays. You see here one building has the planar array, another building has a cylindrical array. Just to see the future of base stations or of the antenna arrays for base stations. Now I come to the concept of how to generate multiple beams using an antenna array. I will revisit, or just refresh your information about antenna arrays. For an antenna array, so I hope that the figures here are clear enough. The axis perpendicular to the array is the z-axis, the horizontal one is x, and the vertical one is y. The patterns shown here are both functions of theta. Theta is the elevation angle which is measured from the z-axis perpendicular to the array. The difference between what is called azimuthal pattern and elevation pattern is whether you cut in the E-plane or you cut in the H-plane. Cutting in the E-plane means you have the cut YOZ, which means phi is equal 90 degrees. And in the H-plane is the XOZ, which means, of course, E and H-plane is now just a convention. So because it depends, it is just history. Okay, I know that I still have 10 minutes. Okay. So these are actually the form of the antenna patterns. How we steer these antennas, we may steer them vertically or we may steer them horizontally depending on the need itself of the base station. Okay, this is the very, very simple expression for how can we derive the antenna pattern, because I need this expression, this simple expression, to explain something later. So my coordinate system x, y, z with the elevation angle theta and azimuthal angle phi, and I arrange the antenna elements in x, y with separation dx in the x direction and separation dy in y direction. You may, if you refer to your fundamental course on antenna, the antenna pattern itself, the electric or magnetic field as a function of r, theta, and phi, theta elevation angle, phi azimuthal angle, is given by this expression. You add together all elements with the excitation factor I, Mn. Imn is the excitation factor of antenna in the space M and N, times this exponential e to the j k naught sine theta m dx cosine phi plus n dy sine phi. Important here is the excitation factor for the individual antenna. The excitation factor is a complex number. It has an amplitude, magnitude A, and a phase alpha. Let us refresh your information about what is the sense of the magnitude A and what is the sense of the phase alpha. The magnitude A can be manipulated by applying windowing in order to decrease the side lobe level, or of course on the cost of the main lobe. So the main lobe will be wider. The phases can be manipulated in order to steer the beam and to create nulls. In general, and you can prove this expression very, very quickly, the phase itself, if it is given by ma k naught dx plus nb k naught dy, you may easily show that the beam itself will look to theta main lobe given by this expression and phi main lobe given by the second expression. Okay. Now imagine the next subject now is how can you produce multiple beams simultaneously for using the same antenna array. If you are going to use the same antenna array and produce multiple beams, you need what is called Butler matrix, or a special form of feeding network. The feed network here shown on the left-hand side has L independent signals, and it feeds M different antenna elements. L and M should not correlate with each other. The problem here, the higher M is, the narrower the beam, independent of the number of the beams. And the number of the beams generated by this antenna array is actually L. This is the number of the input signal to the feed network. So as you see here, L and M are principally independent. Narrow beams and weak crosstalk is achieved by having big antenna or large antenna arrays. The physical systems implementing that are called either Butler matrix or Rotman lens. I will show you just two examples. This is an example of Butler matrix. It is composed of just phase shifters and couplers. You see on the bottom, you have this is special case in which the number of antennas and number of signals both are equal and are equal to 4. But this is not a mass. So you have here 1, 2, 3, 4 input signals, 1 right, 2 left, 2 right, and 1 L, and these are feeding the 4 antennas in order to produce the 4 data streams or mean loops. Okay, this is another implementation which is called Rothman lens. It is a continuous structure in which the beam ports are the input signals, and the output ports are feeding the different elements of the array. Okay, let me now go to the last point in this talk, which is whether we should have all digital beamforming or phase subarrays. For all digital, which is preferred by the communication community, you need one RF front end for each array element. And at the same time, you don't need any Doppler matrix or any couplers, any phase shifters, and so on. This is the pro and contra. Of course, having, say, up to 1,000 elements in an antenna array, each one is backed with RF front, and this will cause lots of problems, at least from the heat point of view. Therefore, the other solution is using phase subarray, in which the digital beamforming is done between the subarrays, so that each subarray needs just one RF front end, but within the same subarray, you use analog phase array using phase shifters, attenuators, and Doppler matrices. So again, this is expressed here. If you look to the factor, to the magnitude AMN in the bottom line, AMN is the multiplication of one analog, which is AMA, and one digital is ND. So I assumed here that your subarrays will be the rows of the array, and within the same row, you have the columns or the elements. These are treated analog by analog fission. The different rows are treated on the digital domain. If we assume such, I hope now that this is clear enough on your screen. The different rows are row number n equals 1, n equals 2, up to n equals n. So you take the digital signal, go to digital to analog converter to one RF front end. And this one RF front end will feed the feeding network of the phase array representing one row. And you repeat this for the all n rows. As you see, the rows are treated digitally. The elements within a row are treated using phase shifters and attenuators. This is actually for just one input signal. Now we come to the much more complicated block diagram here, in which you would like to create simultaneously up to k streams. If you see here on the left-hand side, you have data stream I1 to k. So you have in the digital domain, you have digital signal A1. This digital signal 1 is digitally distributed between the n rows. So you have n equals 1 up to n equals n. Goes through digital to analog converter to RF front end. And these RF front ends now are feeding Doppler matrices, are green here. And the Doppler matrices, each Doppler matrix is fed by K signals and feeding M array. So as a quick comparison, for all digital solutions, we need M times N. M is the number of columns in the array, N is the number of rows. We need for each individual element an RF front end. And we don't need any Doppler matrix, we don't need phase shifters, and so on. For the phase subarray, we need K times N RF front ends. N is the number of rows for this example, and K is the number of data streams you would like to generate. For each row, you need N Doppler matrices. Each one has K input and M output. So just to have a quick comparison, of course, it depends now on how much is K, how much is M, which would be feasible, which is less complex, or which is more complex. This depends now on the situation itself. Let me now come to the last part, which is a conclusion. So I tried to give you a very, very quick overview on the conventional MIMO, multi-user MIMO, and massive MIMO. I also tried to give you very, very quick overview about the relevant specifications of 5G, emphasize the multiple beam operations for increasing the number of independent data streams, and the necessity of using Butler matrix or Rothman lens for that. And at the end of this talk, I tried to compare between two scenarios. One is the all digital beamforming, and the other one is by subdividing the large antenna arrays into subarrays. Within each subarray, we work in the RF domain using phase shifters and attenuators. Between the subarrays, we work on the digital domain, and we perform digital beamforming. Thank you very much. I hope I was clear enough today.
Wonderful. Thank you, Abbas. Very informative. So now it's time for our question and answer session. And we've got a good set of questions here. But before we start that, please remember that you can still submit your questions through the Q&A panel. All right, and please click submit. So here's our first question. So in MIMO, is the data in every channel the same or different?
Depending. If you are targeting diversity, which in order to lower or decrease the bit error rate, you may use the same data set for different data streams. And the receiver itself receives this same data set using different data streams combined together in order to raise the effective signal-to-noise ratio and decrease the bit error rate. This is diversity. If you don't have any problem with the bit error rate, so you have a nice bit error rate and low signal-to-noise ratio, you make use of this resource, multiple channels, just for increasing the data rate by subdividing the original big data rate into sub-data rates and transmitting the different sub-data rates through the different channels. So depending on your application. Am I clear? So Mike?
Yeah, that was clear to me. Yeah, I think that was a great description. Yeah, okay. And also this is a kind of a related question. So are these data streams typically at different frequencies or the same frequency?
For the time being, I would say. Let me think. If the base station itself, there are different scenarios, but up to now, and according to my information, for the downlink, you usually use the same frequency band. Therefore, I think it is for the same frequency band. For the same application, of course, because if you can imagine a multi-purpose platform like your smartphone, you use Bluetooth, you use Wi-Fi, you may use in this case different frequencies, but for the same application, say for Wi-Fi, we use the same frequency. For mobile communication, we use the same frequency. Therefore, I believe that till now it is only for the same frequency, but this doesn't mean technically that you may, this is a restriction, because you may use the same array for different frequencies, but of course, different frequencies means different directional patterns and different so antenna characteristics. But let us assume now it is only for the same band, for the same frequency.
Okay, that sounds good. Okay, so here's another question. With higher gain arrays that have narrow beams, and the narrow beams help minimize the multipath, but at the same time, multipath is needed for MIMO. So how do these reconcile? when you need
yes,
you have
yes,
narrow
I got
beams?
it.
Yeah. Okay.
Yeah, I got it. So, in my opinion, you would need these narrow beams for simultaneous generation of data streams, not for the conventional meaning of MIMO. So the conventional meaning of MIMO relies on multiple reflection, and you really need something like omnidirectional beam. You are right. I believe that the expression MIMO was borrowed from the communication society. The communication society referred to antenna arrays as MIMO, simply as MIMO. For the antenna people, it is phase array. It is just how to generate high directivity beams, which are directed to different users. In principle, has nothing to do with the conventional expression of MIMO. But I think there is some differences between the terminology used in the antenna propagation society, in the microwave theory technique society, and in the communication society. The application I described here, it is just antenna arrays. So how to generate simultaneously multiple beams and to direct these beams to different users using line of sight. You don't use here any multiple reflection. At the same time, I know that the National Instrument, for example, they have one of the test systems now making use of 4 antenna arrays. Each is 64 elements. And these 64 elements are not used to generate high directivity beams. They are used just to generate beams of different antenna patterns, just to maximize the MIMO gain by manipulating the beam form within each subarray, which is for the application I saw 64 elements. They use 4 times 64. And each subarray, 64, is fed independently by phase shifters and attenuators in order to create a beam form of arbitrary form. Beam of arbitrary form. Now, by changing the form of the different beams, which are more or less omnidirectional, they optimize the beam form in order to maximize the MIMO in the conventional sense, which means, which I described here, making use of multiple reflection and so on. This is another application. But you know, the problem is we are now in a time where people are speaking different languages. If you talk with the antenna propagation people, they have their own language with phase arrays, beams, with narrow beam width, and so on. If you talk with the communication society, they refer to the same thing completely different. This is what I believe.
Okay, I think that was a good explanation of the situation. Yeah, you've got to be clear about the particulars of the words that are being used. Okay, so let's see. Here's another I think kind of deep diving question, perhaps, and I'll read it as closely as I can to how it's written. So it says, your theory, especially at the start of the talk, depends heavily on scalar array theory with scalar pure wave propagation modes, which is not fully electromagnetic. What is the current state of our understanding of the fundamental fully electromagnetic theory of MIMO systems? For example, including full polarization, shape, and near-field effects.
Okay, I'm actually an electromagnetic guy. So I'm rather electromagnetic guy than a communication guy. I intentionally used the very, very simple model. Of course, I described the radiation through just one scalar function, just to make things clear. But if you now consider the different polarization of the antenna array, different field components, and all this stuff, just go to the communication society and see which model they are using, because we as IMSP, as MTT people, of course, we love electromagnetics, we love vector fields and all this stuff, but important is the end users. The end users are is a communication society, and if you look to any publication of the or say the majority of publications in the communication society, they use very, very simple scalar model. So therefore, I don't want to make things more complicated than it is needed. And usually, you start with the most simple model. And if this model gives you the results which are coincident with the measurements and with your observation, you are fine. You are done. Don't complicate your lives more than it needs. If your simple model generates different results from your observations or from your measurements, you start to thinking of making it a little bit more difficult. This is what I believe in. Of course, you must also manage vector fields and vector quantities and all this, but no need for the first most simple model, I would say.
I agree with you on that, definitely. Start with a simple model and then make it more complex as you need. So along those lines, though, what could be gained by incorporating polarization into the thoughts here?
So because polarization are orthogonal, so if you now have say dual polarization antenna as your element, because in my model I assumed very, very simple scalar antenna, which means it radiates just one scalar quantity. But say horizontal and vertical polarization or right-hand side and left-hand side polarization, these are usually orthogonal. You may think of these as being additional elements. So say if you have the two polarization within the same element, imagine that you have two antenna arrays, one for the vertical polarization, one for the horizontal polarization. But at the same time, in order to reduce crosstalk between elements and to reduce crosstalks between upload and download, you usually use one polarization at one frequency for downstream, the other polarization together with the other frequency for the upstream. Of course, theoretically, you have the resource. So if you have 64 elements, each is dual polarization, you have 128, effectively 128 elements. But in order to reduce interference and crosstalk, you usually use different polarizations at different frequencies for, say, upload and download. This is engineering issue and not theoretical issue. So from the theoretical point of view, of course, you double your resources.
I think that's a great answer. Yep, that's great, and I think that's also a place to stop here. So, ladies and gentlemen, I'm afraid we are out of time. There are still a handful of questions in the queue, and I believe the presenter will follow up with those unanswered questions offline. As we said earlier, this session will be archived on the Society website at mtt.org. All the registrants will get an email reminder with the website address when it's available. For attendees that would like to receive PDH credits, please follow the link in the webcast view and use the code provided on the last slide of this presentation, for the slide that's shown right now. Once again, I'd like to give a huge thanks to Professor Omar for this excellent and informative presentation. And special thanks to our audience for joining us today. We hope you found today's event valuable and that you'll return for future IEEE Microwave Theory and Technique Society webcasts. Thank you and have a good day.